I'm Sastry Malladi, Chief Architect for Stubhub. How many of you have heard about Stubhub? Quite a few. I'll talk a little bit about that. Today's topic is about data ingestion into Hadoop. And I'm sure you've heard lots of talks on Hadoop and the processing power, but there are some gaps in how people do today ingestion into Hadoop, analyze for their business purposes. I'm going to talk about what we have done and how you can possibly leverage some of that. But before we get into that, what were some of the use cases that we were after, which is pretty common to use cases that many of you may have, and how we identified the gaps, and how we resolved that, what frameworks and solutions have we built, and how we can possibly leverage that. Those are the details I'll get into. I'll spend a couple of minutes, since many of you may not be familiar with as to what Stubhub is, what eBay is, just a couple of minutes on some fun facts and some of the use cases that we've had. Stubhub is an eBay company. It's part of eBay. eBay acquired Stubhub in 2007. We've been part of that since. 25 million plus users. It's an online ticketing marketplace, those of you that are not aware of it. It's similar to eBay, but it's specifically for ticketing industry, right? And I'm not going to necessarily read through all of those, but some of the fun facts include this. Every second a ticket gets exchanged or sold on Stubhub. And lots of data analyzed. One of the important things in this context to think about is terabytes of data gets processed every single day. And the question is, how do we do that? How do we ingest the data into Hadoop? What kind of analysis do we do? What frameworks have we built? And how can you leverage that? So very quickly, historically, Stubhub has been just a marketplace for people who want to exchange, buy and sell tickets out there. We've been expanding since the last couple of years into more of a discovery phase, meaning that you don't necessarily, customer doesn't necessarily know what they're looking for when they come to the site. How do you drive the personalization recommendation so that you can get to really what you want? To do that, you need a lot of data analysis. You need to understand the customer behavior, and this is where some of the use cases are coming in. From this, we had identified 4 primary major use cases. From a buyer standpoint, personalization recommendation in terms of you're in town today, you're looking to do something in the evening. Where do you start? How do we drive you to looking for what you want? Similarly, if you're a seller, if you've got ticket at your hand, you want to price them. How do we guide you to price recommendations based on so many factors, whether it's weather, whether it's demand, and all of that. That requires a lot of data crunching. Social interaction, think about this these days, right? So if you're in town today, if you're attending an event, and if you were to publish that message on social networks, Facebook, LinkedIn, wherever, right? And if we can grab those messages, and if when your friend comes to the site to say, look, your friend is sitting here, is an event, how about we recommend you something there? Again, these are simple problems, but requires a lot of data analysis. Not to mention the traditional business analytics, which is about understanding the business, how we're doing, how the customers are doing. And lastly, the customer 360. You want to completely understand the behavior of the customer before coming to your application, your site, after they've left, or while they're interacting on your site. How do you understand their behavior? What is it that they're looking for? One factor that has more complicated this situation in the last few years was the plethora of these devices the user is interacting with. I might be interacting on a mobile device. Now, a few minutes later, I might switch to my laptop, and I want to continue where I left off. How do we connect these data pieces together for the user so we can provide a consistent and better experience for the users, right? These are use cases. From these use cases, you might think about, so there are today lots of people using Hadoop, lots of people are bringing in data into Hadoop. So what's the problem? Why couldn't we use what's out there already? We could, we did, but we identified a bunch of issues, right? So if you look at today, traditional data warehouses, for example, could bring in structured data. You have ETL processes, whether it's your commercial ETL products like Oracle and Informatica and whatnot. But to ingest and bring some of the unstructured to semi-structured data, such as clickstream, user is interacting on your website, you're clicking all over the place. That's data points. How do you bring that data into traditional data warehouse? You can't, right? So this is where the Hadoop comes in a picture. Same thing for weblogs, same thing for email responses. You send marketing campaigns to people. You want to know who has opened those emails, who has clicked those emails, what was the response. All of the data is not necessarily structured. It's semi-structured at best. How do you bring that? And more importantly, how do you bring that on a regular basis, streaming, automated into your Hadoop process so that your downstream teams can leverage and analyze that data? There are, sure enough, one-off solutions that exist today. For example, take Sqube. You can take your relational data today and pump it into Hadoop as well. And there are some other solutions for unstructured as well. What we're after is to say, how do I automate all of my data sources I've got on a regular basis? Some are stream-oriented, some are batch-oriented. What do I mean by that? Batch-oriented meaning transactional data. For example, every 1 hour, I can pull in my transactional data into Hadoop, right? I wouldn't call that necessarily streaming. But clickstream, as user is interacting all over the place, you want to see the data as it's coming in. You want to stream that data, the down pipeline. So there are many such sources we've got. I'm sure all of you, depending on where you're working, you have similar data sources as well. The second part of it is data validation. As you're bringing in the data, how sure are you that what ultimately ends up in HDFS, which is your Hadoop file system, is exactly the same as where you started with? Well, how can I guarantee that the data that's coming in is the same as what's stored out there? There's no such capability today in many of the existing open source projects. This is some of the frameworks that we built, which allows you to flexibly plug in those validations. And high availability. If stuff happens all the time, things can go down, processes can die. How can you build in high availability where if my ingestion process is down, some other process automatically picks it up, or it generates alerts to people? This is where monitoring comes into picture. So somebody takes a look at it instantaneously and then fixes it what was wrong out there. And this is the monitoring piece that I talked about. And then lastly, one thing I want to talk about is ability to kick off your applications and jobs on when the data arrives. A lot of the times you have cron jobs, you have maybe sometimes UZ processes and whatnot, where you can express that when this data arrives, kick off my application. But what if the data never arrives? The data arrives at, you might have a cron job that says run my job at 9 o'clock. What if the data is not available at 9 o'clock? What do you do? How do you express that instead of expressing it as bring the data at 9 o'clock or run my application at 9 o'clock, when the data arrives, run my application? And by the way, here is a schedule window. If the data does not arrive within that window, raise an alert. So somebody's got to look at it to see what's wrong. These are some of the capabilities we thought were gaps in existing frameworks, and so we decided to build an ecosystem. So the result of that is we built this whole ecosystem, just the framework part, as well as all of the additional bells and whistles that I talked about, monitoring and data validations and whatnot. And we do plan to open source this soon this year. And so you might be wondering, so why am I talking about this here in this open source conference? Because we do plan to open source this soon. And you should be able to, all of you should be able to leverage what I'm talking about here. So let's get into a little bit more the bells and whistles. As I mentioned, I wanted to be pretty clear what it is and what it is not. What it is a data ingestion framework and an ecosystem for data validations and management. It is not a data analysis framework like R or Mayout or Apache Mayout things. It is not that. It is about the frameworks and ecosystems to bring the data. It does not also include any reporting tools. So we got to be very clear about that. This is not for reporting or data analysis. This is to bring all of the data, make sure it's available to people who want to analyze and create the reports. So, the colors don't look pretty good here. So it has multiple layers. If you look at the overall, the system ecosystem, apologies for the color coding here. It's not quite visible, but I'll try to explain as much as I can. So at the bottom of it, something that I'm not showing here is your Hadoop system. That's your HDFS layer, all of your, regardless of which distribution that you're using out there. And then we have existing open source frameworks like Flume and Kafka that have pretty good constructs about source and channels and things and how you bring all of that, right? So we don't want to reinvent any of that. We want to leverage all of that. So what we have built on top is leveraging all of the things that I just talked about. How do I configure and create through configuration to say, look, here is my source that is coming in from web or web HDFS or a JDBC SQL store or a JSON MongoDB store. You pick your source where the data is coming from. how do I configure that source and define all these characteristics in terms of what do I want to be monitored, what do I want to be alerted on. Metastore management, I'll talk a little bit about that later, but primarily metastore management, this is a key unique aspect, is about as data is coming in, how do you make that immediately queryable in your HDFS through Hive or other sources out there? How do you create those meta schemas? And it's easier said than done, because those incoming schemas may not be static, right? If it's a structured data, sometimes, yeah, you can more or less say it's a static schema. Think of it as a clickstream data coming in. Think of it as your JSON documents coming in through other sources. The schemas may not be static, so dynamically changing. How do you handle that? But I'll talk about that in a second. And data validations. This is where we absolutely have to have a framework and consistency. Say, look, I want to be able to tell my data scientists whatever data you see in Hadoop and HDFS is good. It closely matches with what producer produced. How can I guarantee that? And this is where we had to come up with the validation frameworks. And the validation is different for each type of source. It's a different validation for SQL data versus different validation for log data. And finally, high availability that I talked about. Now, the layer, this is what I'm calling, there is a color coding here. This green simply means that this is the existing framework that we're using. This color means that these are the things that we have built. These are the things that we're going to open source. What this color means is kind of a shade of this color. What it simply says that there are some of those things that come out of the box with the framework that we've built. Some of these things you can build when you download. You can build yourself if some of that you want to customize and add. So what exactly is this layer? This whole concept of a handler chain processing work, meaning that think of it as a data pipeline. Data is coming in, and you want to do multiple steps of processing it. I'll give you one example. Let's say there is, clickstream, regardless of which product you're using, data is coming in. It's more often than not, it's a name-value pair. So you have a name and a value. It's a sequence of name and a value. And the data is coming in, let's say it's coming through a file or through a Kafka stream. And at some point, there's going to be a delimiter character to say, look, I've got a bunch of names and values, and this is a new line character, and I'm going to start a bunch of new line values too, right? This is the kind of data that's coming in. One example. Now, you might want to say, look, I want to write a series of handlers to process that, process as in not analyze, but just to bring it into Hadoop. One handler might be, I'm going to read, because the size of the file that you're reading might be gigabytes. You might not be able to read the whole thing into the memory. You need to batch it up. Maybe you have a batch size, buffer size, read it into a buffer, and then process it. Process that buffer. When you're done with it, go back and read the next block, right? Common stuff, nothing rocket science. Now, but this handler might just be doing that. Imagine that this handler does, reads 1 megabyte of data into the buffer, but it may not be exactly integral number of lines per se. It might be maybe 10 lines plus some extra bytes. So what do you do with the extra bytes, right? So you might have to have a next handler in chain that says, look, I've read into the buffer. Now you process it, however many number of lines that you need to process based on the type of data, take it and write it to a channel. Leave the rest of it in a buffer, for example, right? So what I'm getting at is that there is a need for orchestrating a bunch of these handlers together and chain them together, that they work in coordination, and then they can go back in loop. And I'll show you one diagram that actually explains how that works, but that's what this layer is about. A bunch of handlers, and out of the box, we have written handlers for reading name values, reading JSON, reading from a file, reading from JDBC, reading from a Kafka stream, reading from wherever, right? And you can string them together. But you can write your own too. If you come across sources that we have not covered, or if you come across things that you need to customize, you can do that as well. Finally, this is the last layer. This is the key piece, what we're calling data adapters. For each type of source and for each type of data format, you write what is called an adapter. An adapter is really nothing but, in this whole system here, just a configuration. You string a bunch of things together, a sequence of source handlers, a sequence of these handlers that I'm talking about. The handlers are of multiple types, source handlers, sink handlers, we'll get into that in a second, and stitch them together without actually having to write any code. That's the whole concept of the adapter, right? And I'll show you in the last couple of slides how we ourselves are now leveraging this framework to solve the problem that I started to begin, that I stated at the beginning. Is this sort of clear? Is the problem space understood, what we're trying to achieve? Good. The qualities that we kept in mind as we're building this, and again, these are not necessarily rocket science, but some of the key principles that we followed is we wanted to make this to be as generic as possible. This is the data ingestion for any source and type. It should not be specific or hard-coded to a particular type. We wanted that extensibility. And the reuse part of it, as some of the data source adapters that are part of the framework, and some you might be building your own in configuration, but how do you leverage that? As an example, I might have user segmentation data that's coming in, which is, Axiom is one of the companies that produces that, but it doesn't matter which company you use to collect the data. Your clickstream data, the formats are the same. Why would you have to write another adapter to go do that? So you want to be able to just take the same adapter, change the configuration, and you're done. You're ingesting now your user segmentation data that you can combine with the other sources to do your analysis, right? That's the reuse part we kept in mind. And finally, flexibility to export. As you're familiar, most of you are familiar with, after you have ingested into Hadoop, you're doing analysis, you're now producing results. Now you want to publish the results to anywhere else, or even the ingestion itself. Some of the sources, as it's coming in, you just want to put in HDFS and define a Hive schema. Some of the sources you might want to ingest into HBase based on what your use case is, right? Ability to flexibly publish the data as the data is coming in to different destinations. How do we do that, right? That's one of the key things. And finally, high availability and manageability that we talked about, which is it needs to be reliable, and you need to have some sort of a management or console or manageability to see what data is coming in, what the failures are in the system, and things like that. So if you're still wondering what's unique about this framework, we have got some stuff that's out there already in the open source as well as commercial products. So what's so unique about this, right? If you were to remember only a couple of things, here's what I try to state there, right? One is the core framework itself. So what's so unique about the core framework? It does one thing, which comes to the first thing, ability to distinguish the boundaries for the data types and automate them. What do I mean by that? This is the example that I gave you earlier, that as you're reading data, these adapters have no idea exactly what is this data representing, what's the delimiter for their character. So if, for example, a JSON document is coming in, it has no concept, generically speaking, on what's the boundary of a JSON document, right? So you can't just have parallelism to say, well, I'm reading it, I'm going to read the few bytes first, one thread is writing to the HDFS, I'm going to read the next thread is reading the next few bytes and writing to HDFS, and guess what? This could be garbled up. The data in the system ultimately is garbled up. Ability to understand based on the type of the data format that you have and recognize the boundaries for each type of data and process them in the same order and automate it. That's one of the key things in the framework. Now, outside the framework itself are these things that we talked about. It's beyond the framework. Data validation, monitoring, metastore, and management dashboard are the key things. This is the point I want to get across, because I know it's pretty common to think about, look, this is yet another framework, one more framework. Why do I need to do that? Why do I need to use that? This is why we had to do that. These are some of the gaps that we noticed. The guts of the framework, as I described in the architecture diagram, is, again, we are not reinventing the wheel. We're leveraging what's already out there and extending and building on top, right? That makes sense. And in fact, if you have used, for example, Flume or Kafka or Kafka channels, one of those, as you will see in the next few slides, you can actually already leverage the exact same classes that you've already written, plop them into this framework, and that's how we have extended that as well. Orchestrated handler framework, and this is the key here, as I talked about. Ability to orchestrate these handler flows to do that. And I guess I've covered many of those in the previous slide, but these are effectively the gaps, and building on top of this, bridging these gaps. I'm not necessarily repeating them now because I talked about it in the previous slide. Handler framework, data validation, monitoring, and end-to-end manageability, metadata store, immediate queryability. So let's go a bit more technical under the hood. If you actually peel, so how do we actually leverage that, right? Again, apologies for the color coding here. It may not be quite clear, but I'll try to see what I can do here. So many of you who have used Flume, for example, may be familiar with. So these, again, the green color here is the existing code from Flume that you may have. We have interfaces for what are called source and sinks in Flume, those of you that are familiar with it. And then there are abstract classes that come out of the Flume that gives you for different types of sources. So what have we done? So remember the handler framework that I described in the architecture diagram out there? This is the handler interface. And we have, of course, out of the box, we have abstract classes that actually implement all of that. The way we leverage the Flume here is that our own abstract class actually also implements and extends this. And then you can then write your handlers. We have written a bunch of handlers. These are the handlers in the architecture diagram that I talked about that can leverage the Flume, delegate to where the common functionality exists, but actually leverage the rest of the handler orchestration framework that we talked about. That's kind of how we extended it. I don't know if it's obvious by looking at the pictures here, but since it's a bit technical in terms of classes and stuff like that, exact same thing for sync as well. As you can see, exact replication of the sync here. So the key here is that if you currently have either directly using some of the Flume classes or have extended those classes, you would be able to use this handler chain to extend and leverage the same thing that you've already done, but get the additional things that we're talking about. That's where the reuse is coming in a picture. That's what the previous slide was showing about was sources and sinks, right? And here, let's talk about the channels for a second. So normally what happens is any source which is reading the data, after it processes and all of the things that I talked about, ultimately has to write to some channel so that the sync handlers can read from the channel and write to HDFS or whatever destination that you're looking for. And as you can imagine, as you probably are guessing, exact same thing what we did for channels too. If you have, we're leveraging the existing interfaces and build those capabilities that I talked about as an extension on top. We've got our own data channel interface and abstract classes, but delegate that. As an example, so there is a Kafka channel, it's part of the Flume. Actually, now there is Flafka, which is the Kafka channel. Now, it might be using high-level consumer for Kafka, those of you familiar with how that's done. What if you want to have better control on the offsets that you're reading from Kafka, and how do you do that? So this is one example where if you have used this channel interface that we have a Kafka data channel class that actually delegates and leverages a lot of this, but this is where we control the offsets. You can use a low-level consumer to change the offsets if you want. So the key is, again, minimal disruption to what you're already doing, but adding the capabilities that's already out there. And that's what the value add that we created as part of this framework. And same thing for Metastore too. And Metastore has similar classes. Metastore is, again, you might ask, what is Metastore in this whole process? Something that actually does not exist today in open source anywhere is this whole concept where as I'm bringing in the data that I want to, as soon as the data is ingested in Hadoop, I need to be able to go to Hive and be able to do just a SQL query just like anybody else does. Or I need to be able to kick off my Spark or MapReduce job or write a pig script or do anything else you want. How do I manage the schemas for that? I have one slide that I talk about in the meta slide, but that's what this meta story is talking about. Finally, the adapter. This is again a fixed set of classes that come out of the framework. Remember in the architecture diagram I showed at the high level that there is a adapter configuration which is just stringing together a bunch of these handlers. It's just configuration. You don't write code for that because we have written the code that basically invokes all of the, based on the configuration, your handlers, right? It leverages quads for jobs in the sense that, remember one of the things in this concept is there is a source handler chain. You read, some of the handlers are reading the data, and then some other handlers in the next chain have actually put the data into channel, right? That's happening. But who on the other side, in parallel, is reading the data from the channel? That needs to be kicked off in parallel, right? So, and the way to do that, we're leveraging quads for that. So anything that I'm talking about here, this is not something that the code as a user of this framework you would do. This is the framework code itself. As a user of the framework, you would not write any of this code. You would configure your adapter to say, here are my sources, here is my destination, here is my thing, ingest and validate. That's what you would do. Now, it's just a bit more on how that handler flow works, right? So I'm actually going to that side. I can't see from here. Am I blocking you guys? You can see? So remember the adapter, the configuration that I talked about, it starts the handlers. There is a concept of source handlers and sink handlers that we talked about. So let's say you have a series of handlers. You have, just assume for a second you have two handlers. One handler is reading into a buffer. Second handler is processing that for the data boundaries and so on, right? Now, but you want to do it in loop until the entire data, for example, is ingested. So what the handler chain framework does, again, this is part of the framework code. For each handler that it runs, it invokes the handler. Obviously, if it's a failure, it's going to handle exceptions and raise the alerts and exit from there, right? This is another capability not to be taken lightly. Ability to raise alerts to people that need to know when things have failed. Now, let's talk about the positive case where if it's successful, you invoke the, now the handlers have the ability to inform to the caller to say, look, I'm not done with my job yet. I've read, but I've left some bytes still in the buffer, or there's still some more bytes in the source. So call me back when you're ready at some point, right? So they can indicate to that. When they indicate to that, we journal that information and then move on. Regardless of whether it needs to be called back or it doesn't need to be called back, we move on. And then and we check, is it a last handler, right? So if it's a last handler, obviously, so then then you check in the journal to say, look, I'm done running through one set of series of handlers done. Is there anything I need to go back and call back? And then it goes into the loop there, right? And then the whole thing continues. On the other hand, if there is nothing in the journal to do, it's going to exit and you're done for this part of the ingestion, and then it goes back to the loop again, right? This is the key part of it. Handler chain, orchestrating these handler chains where somebody does not need to manually run a script, somebody does not need to manually remember when the data is going to come or when the data is done ingesting. This goes in a loop like that. This is the kind of orchestration that we talked about. And this ability to express for each of these handlers on when they're done, when they need to be called back, and how the process is automated for that. The other side of it, remember I was saying that one of these handlers is going to write the data to a channel, but who reads it from the channel? Who's there to read from the channel? So this adapter, in parallel, at the time it initiated it, through spawning a different background thread, start this sync handlers as well. And it goes through the exact same process. Start reading it. This is how you kind of automate that the impedance mismatch, because there is naturally an impedance mismatch between the readers and the writers. The reader might be faster, the writer might be slower, or the reader is slower, the writer might be faster, right? You have to manage this impedance mismatch. This is how the impedance is mismatched. Or resolved rather, not mismatched, but. So remember I was telling you meta store. So what are some of the key things in the meta store that we talked about? Here is the single most important thing. Let's assume that you have data coming in. It has some schema, it has some name values or whatnot. The key is you have no control, you as in the data ingestion framework, you as in the data ingestion layer, have no control on when and how the source schema changes, because somebody else is controlling that, what the schema changes out there. But your framework has to automatically work if and when the source schema changes, there are more data elements coming in, the framework should automatically still know that. So you might think, hey, why is that a problem? Just take whatever comes. Why is that a big deal? It is a big deal. Here is why. Supposing you have 15 fields to begin with in the original schema. So you are ingesting in that order, those 15 fields. You ingested that. And you defined in the meta store automatically the schema for it, somebody can query. 2 days later, somebody changed the original source schema. Say, there is two more elements. Maybe one more element was deleted from the existing one, 2 more elements were added. Now, if we just ingest exactly those 15, now back into how we did before, the whole data is messed up. When somebody tries to query it, orders are messed up, right? Ability to remember what you have seen before And as the data is changing through the schema, understanding where the next set of columns are coming in and remembering them and being able to update the schemas. That is a key aspect in metadata management out there. So what are we trying to solve here? We're trying to solve the problem of data ingestion does not end when you just bring the data and dump it into HDFS, because it needs to be usable. It needs to be queryable. It needs to be easily usable by people. And that's what this meta store is trying to solve. An ability to dynamically update that. Preserving the types. Here's the other thing too. Data types, particularly for SQL structured data, you might have a number, you might have a string, you might have a big decimal, you might have a float, all of that. As things are coming in, how do you create your schemas that actually preserve the same data type as the original data type that you have got, so that when you want to just put up a pig script or a SQL query like Hive, it actually works out of the box. And this is where the immediate queryable to Hive comes into picture. And then auto creating partitions, right? This is again ease of use. Partition could mean, it could be date, today's date. Partition could mean it's an hour. Partition could mean 10. It's you define what's the partition mean for you based on the size of the data, right? Because the whole thing is not one single file in HDFS. You want to partition that so that your jobs, whether it's a Spark job, MapReduce job, Hive, Pig, whatever your favorite tool that you're using, can easily work through and slice and dice the data that you want. And finally, exposing this metadata through a REST API so that you can have a management console that actually tells you and can control and define some of this metadata. So these are the key things of Metastore that we're talking about. Now, I'll show you the next few slides. Again, remember the architecture slide, that is the key slide to remember. Different layers. You have Flume, you have the framework, ingestion framework, the handlers, and finally the top layer, which is the adapter configuration. Adapters. Adapters are nothing but just a bunch of configurations. You don't actually write any code for it. This is what a typical anatomy schema for an adapter looks like. You give it a name and give it a type. These are two different options. Is it a streaming adapter? Is it a batch adapter? And it has some meta information. We'll go through that a little bit in a second. So this is the adapter, generic adapter info, right? The name and the type of the adapter. And this is about the source handler details. What's your source and how you want to process that. This is a channel information. And finally, this is the sync information. So it really has 4 sections to it. You create and concept an adapter by putting these 4 different configurations together. That's your adapter. So we'll go examine this a little bit in detail. So what does meta configuration do? Meta configuration is essentially some of the examples here. This is not exhaustive that I'm showing here. Is that as data is coming in, you have an option to express. Do you want to automatically update the Hive schema for that as data comes in? You might choose not to do that for various reasons, but you can express that. You can also express, like inform the adapter to say, where is the schema for the incoming one, and where is my bookkeeping directory? Where can I bookkeep it to say, what have I seen before, what am I seeing now, and what's the delta, right? These are some of the things that, and what's the data, what schema should I create, and what's the DB name and all of that, right? Same thing for, I'm showing 2 different examples here. This is for one type of source, this is for a different type of source. So effectively what you're telling is you're configuring the Metastore, all of the things that you would normally write code and lots of things on top of that, you would use this configuration to express that. Source configuration, pretty similar to, so I'm giving an example here that I've got a tracking source. Tracking is, think of it as a clickstream data source out there. And I'm expressing 2 handlers here in my source. I've got one source, and here is the sequence of handlers that I'm expressing. One handler is what we're calling an input reader. Another handler I'm calling an input processor. The job of the input reader, as the example that I've been giving throughout, is to, in this case, was to read, for example, a block of data from a file and then put it into a buffer. I'm oversimplifying it. And the next handler would say, now I start processing that block and leave some bytes. It's a circular pointer buffer if you think about it. One guy is reading and putting into the buffer, other guy start reading into the buffer. It's a circular buffer, they're exchanging that, right? And how do you coordinate that? And I showed you the framework handler flow diagram and how the coordination between these 2 happens. And again, these are sample configuration just to get an idea how things are working. Channels, I'm giving a couple of examples. A memory channel and a Kafka channel, for example. And information for each of the types of the channels is different. You're expressing that in the case of memory channel, you want to say what's the capacity for each total memory and the buffer sizes and so on. And then here you're expressing Kafka topics and hosts and whatnot, right? So again, the key last thing, sinks. Sinks also, remember, exact same thing, the opposite reverse of the source handlers. I have a couple of different handlers that are defined here in the sink. Again, I'm calling tracking sinks. Remember my example I gave you, tracking source. Data is being read from tracking. Here, now that same data that I've read, now I'm writing to a sink. And in this case, HDFS. But I've got two handlers to do that. One is first a JSON Hive schema mapper, and then the second handler is web HDFS. What it means is that this first handler is reading now from the channel that my source handler, the last handler in the source chain has written, and the first handler is trying to map it. Now I'm receiving, it could be an Avro schema or it could be just pure text JSON that's coming in. Now I need to somehow map the elements that are coming in, because there's no order of guarantee when you bring it into in JSON schema, to my Hive schema, how I map that, and write into that map layer. That's what this does. And then the second guy comes in and puts it in a buffer. Second guy comes and says, okay, as you're doing this, I'm taking these bytes and putting into HDFS through web HDFS interface and writing to that. This could very well be, it could be another handler that says, I can put it into multiple. This is the other key. You might say, this similar things exist in other frameworks, whether it's Goblin or some other things that you look at. The key here is the ability to configure multiple of those. What if you want to have the same data going into multiple different destinations, right? That capability exists here, because it's a matter of adding more handlers and adding that synchronization. That's basically it. So if we look at the end of the day, people who actually want to use this framework would be creating these data adapters through that configuration on the top. What comes out of this, out of the box, is we have support for handlers for different data formats, name value pairs, clickstream, SQL, JSON, as well as source different types, whether it's file, JDBC, web HDFS, and Kafka, and so on. And of course, you can always extend it through other sources. Now, the last thing I will talk about is, great, we built this framework. Now, how are we using it ourselves in Stubhub? Remember, I talked at the very beginning what our vision was, what problems we're trying to solve, and now we deep dived into actually what solution we built. Now I'll go back to say, look, how are we using that solution to solve the problem that I just talked about? So everything that I just talked about is this box right here, plus this. This box is that whole framework that I described and up until now. Now, we have different data adapters that are created through configuration on top of that. Data is coming in, transactional data, clickstream, social, weblogs, catalog, you name it. We have lots of those sources coming in. We have different configurations to that. The data gets ingested automatically on a daily basis to Hadoop HDFS right here. This is your Hadoop HDFS. And on top of that, and of course, we have people use different flavors of analysis frameworks. You pick your choice. What we also do for the purposes of supporting existing traditional business users that still want to be able to see some of the transactional data coming through traditional data warehouse, we have a process that automatically also ingests into the traditional data warehouse. That just as a point, so that existing users can continue to use that. And these frameworks can now publish the data results into HBase and Solar as well, which is a search engine. We use Solar for that. So this is how we're ingesting data back in here. People are analyzing it and producing the results back into putting where they need to do. Now what? Okay, you analyzed it, you ingested it, people have written solutions. Now what happens? So that same information now, this what I'm calling the OLTP world, this is our website or online marketplace through native apps and through website and whatnot. The results can be replicated back into Solar here. We have HBase here. These results are replicated here. Now here is where we have lots of services, microservices, all the business logic services and whatnot. As an example, in this case, recommendation. Remember, one of the first use cases that I talked about was recommendations. How do you recommend to people on Stubhub as user comes to? So if the data is coming in, all of the user interaction data, people are analyzing it. This is the batch stuff. I'm not showing Stream here. Stream is a different path. And then the data gets replicated here. Our recommendations API, for example, looks at the results from HBase and Solar and immediately reflects it back onto the website. The user actually sees that. Now, the other use case that we have is that some of the data scientists, they want to do a lot of modeling, fraud modeling, analysis, recommendations, and all of that. They may not want to do that analysis directly on this data here. So what we do is we also create a separate analytics cluster for them. Then there we have installed their favorite tools, for example, in Apache Mayout or Apache or in Oracle R and whatnot, right? And they can use their favorite BI tools too. There are a bunch of BI tools on top of this as well, which is one area where Hadoop still is maturing. This is kind of how we use that. So to recap, we have a problem to solve. We identify what the gap was. And we actually built that framework. And I've then just showed you how that same framework that we built, now we're leveraging to use this problem that I started with. And we do plan to open source this soon. So you should be able to leverage this sometime soon. That's what I've had. So we have a booth over there. Please do, when you get a chance, please do visit our booth. And there are more. We work on lots of technologies, and we plan to open source and some of those as well. So please do stop by our booth and learn more about it. And we're hiring. So if anybody's looking for lots of technology jobs, we're hiring. So please take a look at that. I'll hang around after this as well. If you have any questions, I can, depending on how we're doing in time. Yeah. Thank you.